So what I want to talk about is a little bit of a follow-up on what Daniel told this morning. And I would like to reframe the GOLT as a theory of optimization. And I think the challenges Daniel has already talked about to the GOLT, I think many of them are understandable. A theory with limitation in the title, I think that is difficult to explain intuitively to biologists and maybe to other scientists. And I think this intuitive contradiction between limitation and optimization, I think that's something we should also take serious and attempt to explain better. In a recent paper, Douglas Glazier has talked about a shift from metabolic theories that explain metabolic scaling from Newtonian, as you called it, to Darwinian. And I think the GOLT is clearly a Darwinian theory on that scale. So how can we bridge this, or how can we better explain or overcome this intuitive contradiction between limitation and optimization? So I want to talk about constraints and optimization, how we think of constraints as part of optimization strategies, and then talk about optimizing maintenance and production, and then focus on the crucial importance of distinguishing between intra- and interspecific explanations of metabolic scaling. And I think in the literature about the GOLT, these two categories are often blurred. This is a quote from a colleague, and this is not a criticism, but I think we should really take it seriously. So Osteonitis, he says in a paper from some years ago, so from an evolutionary perspective, an intrinsic inability to develop mechanisms for adequate oxygen supply seems unconvincing. And I think we understand why that is. So why should there be a certain limit where nothing goes any further anymore? In another paper, Lefebvre, she says, so in our field, in physiology, we generally assume that demand determines supply, not vice versa. So when there's demand for more, then some optimization strategies will provide more supply. What underlies such assumptions? In a paper from a few years ago, Marshall and White responded to the GOLT by saying, this is the title of their paper, aquatic life histories are not shaped by selection, are shaped by selection, not oxygen limitation. And as if this were a contradiction. It's a bit like if we say the stability of roof construction is shaped by architects or engineers, not by gravity. So this confuses, I think, two distinct types of causality. So roof constructions have to work with gravity in order to work. So how do organisms optimize their functioning? If we look at the definition by Lotka to 1922, which formed the basis of the maximum power principle, he says natural selection tends to make the energy flux through the system a maximum, and then he adds, so far as compatible with the constraints to which the system is subject. And he goes on, so in the future we should better explain what constraints are, of course. And constraints in this case are not hindering the selection for better energy flux, but they belong together. If you have just, so this quote may be incomplete without the further explanation by Lotka, so if you just increase energy flux through a system, it will not optimize very much because the energy needs to do stuff. If I have a flute and there's no membrane in it, it will make no sound, it can do no work. So I need to put a membrane actually constraining the flow of energy. So constraints are important, so constraints are used in the system to actually allow the system to do work. And first I thought this may just apply to for example, the internal constraints once energy is already produced in the body. But I think it also pertains to how gills and the buccal cavity works as you could say, a subsystem of an organism. So water, as you all know, water is taken in, and in many fish species, you have this oral valve, it's closed. There's put pressure on this buccal cavity, and the gills actually constrain the flow of water through the operculum. So water is constrained here. And if you look at this from a perspective of gill oxygen limitation, there are actually three constraints involved. So the flow of water is constrained. You constrain it too much, because then there will no water flow through. If you constrain it too little, the oxygen cannot be taken up. And the second constraint is then getting the oxygen into the gills. And there's also a third constraint. So if the gill size also determines how much internal surfaces of little vascular tissue can take up the oxygen. So these constraints are actually controlled. And in more recent theoretical literature, I think these constraints are taken more seriously. So work, of course, energy input is not entirely, you could say, resource input here, which produces any energy and then is translated into, is transformed to work. And this work actually produces new constraints, what Stuart Kaufman called the work constraint circle, or Monteville and Mossiot talked about organism as dependent on the closure of constraints to produce new constraints. And I think this is a highly sophisticated optimization strategy. In the book, actually, we don't talk that much about geometry. These are just geometrical constraints, and saying that the exponent of gill surface area is lower than 1 only says here that this system is not scalable infinitely, that there must be some end to it on an ontogenetic level. But there are, of course, many other constraints. Think about osmoregulation. Gills, and some authors argue that gills first evolved not to take up oxygen, but to regulate or for osmoregulation. There's also the role of parasites, and the next paper will be about that. So these are all factors that result in a trade-off, or in several trade-offs. But there's a different perspective on optimization here. And as White et al. 2 years ago argued, so we can actually explain metabolic scaling without putting any emphasis on constraints. Everything can be explained by optimization. How do they come to this assumption? So they say production, here on the red and blue, always remains constant over the entire life history of an organism. It's never reduced. But the optimization is here a life history or an ecological optimization by switching from growth to reproduction. How does this reasoning work? You need to assume here that maintenance costs decrease over the course of life history. This is why the white corner here on the diagram, this will always decrease. You should, of course, also ask yourself, why couldn't evolution optimize this model here in the sense that growth and reproduction occur further? But what do we have to make of the idea that maintenance costs decrease? We are here in Greece, and you all know this story about Theseus' ship. Theseus, the king of Athens, and during the commemoration of his deeds, a ship was sent to the islands and returned every 100 years, every few hundred years, according to the story. And this ship needed maintenance. And the question is then the philosophical question asked by Plutarch: what is left of the ship if we have done this cycle thousands of times, and all the parts of the ship are being replaced over these hundreds of years? The mast is something else, all the pieces of wood are something else. The ship is something else, right? And the older the ship gets, the more maintenance it would need, not less. Putter, in explaining the right term of the equation Daniel showed this morning, in a later book than the 1920 essay, put it like this, and I love this quote here. He says, "On my desk there's a piece of lava from Mount Vesuvius' great eruption of 1906, and to this day it consists of the same atoms that came together 17 years ago in the glowing maw of the volcano. And when my children will take this piece of memory as a great spectacle of nature into their hands, in a few decades they will still touch the same material as I touched today. A faithful house companion of mine is an Airedale Terrier. He is in his 10th year and has thus reached the threshold of old age. When I stroke his graying fur, I'm not touching the same material parts that once made up the fur when I first made his acquaintance, and even the teeth are not the same, and they are made of different atoms." I'm not sure about the teeth, but just for the sake of the argument. "And even the hand that strokes them is no longer the same." So everything is replaced all the time, and that's how he explained the right term the maintenance term of the Putter equation. And it can be specified to protein denaturation maybe, but everything that's lost. And there's no mechanism to explain here why these costs would decrease with size except for allometries of organs. If you have larger brains in juveniles, of course, that's more costly, but for structure, not for reserve, that should be assumed as roughly proportional to body size. And then we end up with the P-diagram here on the right side. So if you follow the White model and other similar models, and you assume that maintenance costs decrease with size here, then you come to the interpretation by Schäufele et al. Here, where they say, can you put it down again? The scaling exponents of GSA and SMR, so metabolic rate and gill surface area, scale proportionally, and that would be a refutation to the GOLT. How do they come to this assumption? So they look at measurements of metabolic rate. We looked at all the papers that were cited to build this data set. And then they say, well, we see that everywhere gill surface area and metabolic rate scale isometrically. But if you look at what these papers do, they look at respirometry experiments and what grown animals actually consume here. And they didn't look at costs of growth. As Rosenfeld and other authors have shown, fasting fish, 24 hours to 36 hours is not enough to exclude all the overhead costs of growth. So these are included here. So the costs of growth, that would be here in the white area of the left diagram, they are included there, right? So what the GOLT needs to do, and I think this is why the GOLT really depends on adaptionist or optimization arguments, is to look at the distinction between inter- and intraspecific scaling. So what we see here is Kleiber's law. This has fascinated people since the 19th century, and different authors in the early 20th century have looked at different, or have proposed different exponents here, 2/3 or 3/4 here. But I mean, these scaling laws are real, right? We see them everywhere. But we have to assume here, if the GOLT is to hold, that different mechanisms are at play here. So on the right side, we have intraspecific scaling, a fish from larva to adult. And here we have intraspecific scaling from grasshoppers to elephants. What are the different mechanisms here? And I think according to the GOLT, we have to say, so intraspecific, the most important factor is the allocation from growth to maintenance. Maintenance also, in this interpretation, resynthesizes or synthesizes proteins, but they can no longer be used for new tissues, but they are there to replace what is lost here. On an interspecific level, and I think that's what we saw earlier, we have to assume selection and optimization for lower maintenance requirements to explain this. And I think the simplest argument here, imagine the metabolism of a mouse in an elephant. The elephant would overheat and explode and could not function. So the organisms, in order to get big, need to be adapted to these lower metabolisms by using other enzymes and other strategies here. So where does optimization take place? So on an interspecific level, uptake capacity and efficiency are regulated, are selected for. Resource allocation is optimized. And of course, in order to get big or stay small and follow different life histories, maintenance demand needs to be adjusted to the specific species and lifestyle. And ontogenetic, intraspecific lifestyle adjustments, prey shifts, habitat shifts are important. And Daniel showed a few of these examples this morning. And of course, also the minimal impact of gill modification, right? In Leiden, there was a thesis defended a few years ago that looked at gill modification and showed that cichlids could modify on a plastic level their gill surface area very rapidly, so they could make their gills extremely huge, but they could not take up much more oxygen because these gills constrained the flow of oxygen too much. So, as a conclusion, I think maybe the GOLT could also it could also be named oxygen optimization theory, and maybe it would have had less lash back then. But I think to understand this from a perspective of optimization helps us also to explain the apparent differences here. And of course, I think without optimization explanations, we cannot really explain the difference between intra and interspecific scaling. That's it. Thank you for your attention.